Nothing is happening. That is not a figure of speech, and it is not a claim about how busy the universe is. It is a statement about the equations. Search through the mathematics that governs modern physics, the field equations of general relativity, the wave equation of quantum mechanics, the laws describing every force we have identified, and you will find no term for the passage of time. There is a variable called time. It sits in the formulas as a coordinate in exactly the way that height and width and depth sit in them. But nowhere is there anything that moves along it. Nothing in the mathematics ticks, nothing advances. The equations describe a shape, not a story. This is one of the quietest problems in science, and one of the largest. Every human being who has ever lived has reported the same experience, a present moment, arriving, passing, replaced. It is the most universally attested phenomenon in history, and our best description of reality does not contain it. Physicists have responded to that gap in two ways. Some argue that the flow of time is real, and the equations are incomplete, that something essential is missing. Others argue the opposite. They say the equations are telling us the truth, and that the past, present, and future all exist together in a single fixed structure, unchanging, complete, containing every event that has ever occurred and every event that ever will. That second position has a name. It is called the block universe, and it is not fringe. It follows step by step, from measurements taken in laboratories with aluminium ions and from clocks carried aboard orbiting satellites. Where those steps lead is what we are going to trace. To see how strange that absence really is, it helps to look at where the time variable came from in the first place and what it was built to do. The modern habit of writing time into an equation begins with Isaac Newton in 1687 in the work known as the Principia. Newton needed something to measure change against. If a stone falls, the description of its fall requires a quantity that increases steadily and independently while the stone's position changes. Newton supplied it, and he was explicit about its nature. Absolute time, he wrote, flows equably without relation to anything external. It was a background, universal, indifferent to matter, the same everywhere and for everyone, a cosmic metronome that no experiment could influence and no event could disturb. That definition worked extraordinarily well. It carried physics through the description of planetary orbits, tides, pendulums, projectiles, and the structure of the solar system. But notice what Newton did there. He did not derive the flow of time from anything. He asserted it in prose and then wrote a symbol into his equations to stand for it. The flowing was a description of the symbol, not a property the mathematics could produce or test. Take Newton's laws and strip away the accompanying paragraphs, and what remains is a set of relationships between positions and a parameter. The parameter has an order. Later values come after earlier ones in the sense that they are larger, but nothing in the mathematics moves from one to the next. This distinction sounds like a quibble until you examine what happens when you reverse the parameter. Take the equation describing a thrown ball and run the time variable backwards instead of forwards. The result is not nonsense. It is another perfectly valid trajectory, a ball rising from the ground, slowing and settling into a hand. Every step obeys the same laws with the same rigor. The mathematics has no preference between the two. It does not flag one as real and the other as impossible. Both are solutions, equally legitimate, and the equation is completely indifferent to which one you call the future. Physicists call this time reversal symmetry, and its reach is remarkable. It holds for Newton's mechanics. It holds for the theory of electricity and magnetism that James Clerk Maxwell assembled in the 1860s, which describes light itself. It holds for general relativity, Einstein's account of gravity and the shape of spacetime. It holds, with one narrow exception we will come to, for quantum mechanics. Across the entire foundational structure of physics, the fundamental laws do not distinguish forwards from backwards. They permit both, describe both, and choose neither. Consider what this means in practice. Film a pendulum swinging in a vacuum, then play the recording in reverse, and no physicist can tell you which version is the original. Film two billiard balls colliding on a frictionless surface, and the same holds. Film an electron scattering off a photon, reverse it, and the reversed process is a real process that occurs in nature. At the level of individual interactions, the world has no grain. It looks the same in both directions. Yet nobody has ever watched a shattered cup gather itself off the floor and leap onto a table. Nobody has watched smoke pour back into a cigarette or an egg unscramble in a pan. The asymmetry we live inside is total and unbroken. Every memory we possess points one way. Every expectation points the other. And it is not written into the laws. This gap between symmetric laws and an asymmetric world is not a small anomaly waiting to be tidied up. It is a structural feature of physics that has been recognized for well over a century, and it is the first serious clue that our intuitions about time are describing something other than the fundamental architecture of reality. There is a second clue, and it is subtler. Look at how the time variable behaves inside the equations, rather than what it stands for. In Newton's mechanics, time is a parameter, an input you feed in to get an answer out. You choose a value, the equation returns a position. Choose another value, get another position. The equation does not care what order you ask in. You can compute where the planet will be 1,000 years from now before computing where it was yesterday, and the mathematics will not object. The equation is not generating the future from the past. It is a rule that relates every value of the parameter to every corresponding state, all at once, as a completed relationship. Pierre-Simon Laplace pushed this observation to its logical end in 1814. He proposed an intelligence that knew the exact position and momentum of every particle in the universe at a single instant, along with all the forces acting between them. For such an intelligence, he argued, nothing would be uncertain. The future and the past would both be present to its eyes. It could compute forwards to the end of the cosmos or backwards to its origin with equal ease, because the equations run just as smoothly in either direction. Laplace intended this as a statement about knowledge and prediction, but it carries a heavier implication. If the state of the universe at one moment fully determines its state at every other moment, then in what sense does the rest of it need to happen at all? The information is already there. The future is not being generated, it is being read. You can hold that thought and still insist that the reading takes time, that the universe must actually grind through each configuration in sequence. That insistence is not unreasonable. It is what everyone believes, and it is what the world appears to demonstrate every second. But it is an addition to the physics, not a consequence of it. The equations supply the structure. The grinding is something we supply. Now the strangeness deepens, because the exception to time reversal symmetry, the one narrow place where the laws do notice direction, turns out not to help at all. In 1964, James Cronin and Val Fitch ran an experiment at Brookhaven National Laboratory studying particles called neutral kaons. Kaons are unstable, produced in high-energy collisions, and they decay in a matter of billionths of a second. What Cronin and Fitch found was that a small fraction of these decays, roughly 2 in every 1,000, violated a symmetry that had been assumed to hold absolutely. The violation was tiny, and it was real, and it earned them a Nobel Prize. Combined with a deep theoretical result about the structure of quantum field theory, it implied that the weak nuclear force must also treat forwards and backwards time slightly differently. That implication was confirmed directly. In 1998, the C.P. Lear collaboration at CERN measured the asymmetry itself, comparing the rate at which one kaon state converted into another against the reverse conversion. The rates differed. In 2012, the Babar experiment at Stanford did the same with a different particle system and found the same result with far greater precision. Time reversal symmetry is not exact. Nature does, at the finest level, possess a slight directional grain. Here is why that changes nothing. The effect appears only in the weak nuclear force in exotic particles at scales and energies utterly disconnected from everyday life. It plays no role whatsoever in why cups break, why memories accumulate, why coffee cools, or why you cannot recall next Tuesday. The asymmetry we experience is overwhelming, universal, and continuous. The asymmetry in the laws is a whisper, confined to one force acting on a handful of unstable particles. You cannot build the arrow of time out of it. The scales do not remotely match. So the gap remains, and it has been examined by very serious people for a very long time. Ludwig Boltzmann spent the last decades of the 19th century trying to bridge it, and his answer, that the arrow arises from statistics rather than from law, from the overwhelming number of disordered arrangements compared to ordered ones, remains the best answer we have. We will follow that argument in detail because it is powerful and because it does not do quite what people usually think it does. What matters now is that Boltzmann's solution locates the direction of time in the arrangement of matter, not in the fundamental equations. Even the leading explanation of time's arrow concedes the point. The laws themselves do not flow, which brings us back to the shape of the problem. We have a mathematics in which time functions as a coordinate, a dimension, an axis, something you have a position along rather than something you travel through. We have laws that permit both directions equally. We have a determinism that suggests every state is already implied by every other. And we have an experience of passage so vivid that questioning it feels like questioning whether we exist at all. For most of the 19th century, this tension could be managed by holding Newton's absolute time in the background. However odd the equations looked, everyone still shared a single universal now. The metronome ticked for the whole cosmos at once, even if no formula mentioned the ticking. Simultaneity was absolute. Two events either happened at the same moment or they did not, and every observer in the universe would agree. That was the last load-bearing assumption holding the intuitive picture together. In 1905, a 26-year-old patent clerk in Bern removed it. The patent clerk was Albert Einstein, and the assumption he removed had never been examined because it had never seemed to need examining. Simultaneity, the idea that two events either occur at the same moment or they do not universally for everyone, is not a theory. It is the water we swim in. Einstein's achievement was noticing that it is an assumption at all and then discovering that it is false. He arrived there by taking two facts seriously and refusing to compromise on either. The first was old. It goes back to Galileo in 1632, and it is called the principle of relativity. Galileo asked his readers to imagine themselves below deck in a ship moving smoothly across calm water with no windows. Butterflies fly. Water drips from a bottle into a basin. Fish swim in a bowl. You toss a ball to a friend, every one of these behaves exactly as it would on shore. There is no experiment you can perform inside that cabin that will tell you whether the ship is moving or standing still. Motion, as long as it is steady, has no local signature. The laws of physics are identical for anyone moving at constant velocity, and there's no such thing as being absolutely at rest. The second fact was new, and it came out of Maxwell's equations. When Maxwell assembled his description of electricity and magnetism in the 1860s, the mathematics produced a wave, a self-sustaining ripple of electric and magnetic fields propagating through space. The equations specified the speed of that wave. It came out to roughly 300,000 kilometers per second, which matched the measured speed of light closely enough that Maxwell concluded light was that wave. This was one of the great unifications in the history of science, but it created a problem that nobody could solve for 40 years. Maxwell's equations gave a speed. They did not say relative to what. Every other wave physicists knew about traveled through a medium, and its speed was measured relative to that medium. Sound moves at a fixed rate through air, and if you run towards a sound source, you meet the wave sooner. So physicists postulated a medium for light, the luminiferous ether, filling all of space, and assumed the speed in Maxwell's equations was the speed relative to the ether. That assumption was testable. The Earth moves around the Sun at about 30 kilometers per second, so it should be sailing through the ether, and light traveling in different directions relative to that motion should arrive at different speeds. In 1887, Albert Michelson and Edward Morley built an instrument in Cleveland precise enough to detect the difference. They split a beam of light, sent the halves down perpendicular arms, bounced them off mirrors, and recombined them, watching for the interference pattern to shift. as the apparatus rotated through the supposed ether wind. It did not shift. They repeated the experiment at different times of day and different seasons, when the Earth's motion through the ether would have pointed in different directions. Nothing. The result has since been reproduced with modern equipment to a precision billions of times finer, and the answer never changes. Light travels at the same speed, regardless of how you are moving relative to it. This is where Einstein diverged from everyone else. His contemporaries treated the result as a puzzle about the ether. Perhaps the Earth dragged it along. Perhaps moving objects contracted in just the right way to hide the effect. Hendrik Lorentz worked out mathematics that produced the right answers by assuming exactly that. But he regarded the contraction as a physical distortion caused by motion through a real medium. Einstein threw out the medium and kept the two facts, treating both as fundamental principles rather than problems to be explained away. Principle 1. The laws of physics are the same for all observers in uniform motion. Principle 2. Light travels at the same speed for all of them, regardless of the motion of the source or the observer. Hold those two together and something has to give. Speed is distance divided by time. If two observers moving relative to one another both measure the same light beam and both get the same speed, and if they cannot both be measuring the same distances in the same intervals, then the distances and intervals themselves must differ. Space and time are not the fixed stage, they are the flexible quantities. The speed of light is the rigid thing. The consequences unfold with an almost brutal logic, and the deepest of them is the one that dismantles Newton's universal now. Picture a railway carriage moving at high speed along a straight track. A passenger stands exactly at the midpoint of the carriage, and at a chosen instant, a flash of light is emitted from that midpoint in both directions. To the passenger, the situation is symmetrical. The front wall and the back wall are equidistant. Light travels at a fixed speed. The two flashes arrive at the two walls at the same moment. For the passenger, those two arrival events are simultaneous. This is not a matter of interpretation or opinion. It is a measurement, and it is correct. Now, stand beside the track and watch the same carriage pass. You also see the flash emitted from the midpoint. You also see the light travel outward at the same fixed speed in both directions, because that speed does not care that the carriage is moving. But in your frame, the carriage is moving forwards during the light's flight. The back wall is rushing towards the point where the light was emitted. The front wall is running away from it. The light, therefore, has less distance to cover to reach the back wall and more to reach the front. It arrives at the back first. Both descriptions are correct. There is no experiment, no measurement, no perspective that resolves the disagreement, because there is no privileged frame from which to judge. The passenger is not wrong. You are not wrong. Two events that are simultaneous in one frame of reference are not simultaneous in another, and no frame has authority over any other. This is the relativity of simultaneity, and it is the single most consequential idea in this entire subject. Notice precisely what it destroys. It does not merely say that clocks can be miscalibrated, or that light takes time to reach us so we see things late. Those are trivial effects that any careful observer could correct for. This is deeper. After every correction has been applied, after every signal delay has been accounted for, two observers still disagree about which events belong to the same moment. The disagreement is not about perception, it is about the structure of reality, and if there is no fact about which events happen at the same time, then there is no such thing as the present moment of the universe. There is only your present and mine, and they are different sets of events. Newton's cosmic metronome does not slow down or speed up, it ceases to exist. The rest of relativity follows from this, and every piece of it has been confirmed. Moving clocks run slow, verified in 1971 when Joseph Haffel and Richard Keating flew cesium clocks around the world aboard commercial airliners and found the predicted discrepancy of billionths of a second, and verified continuously, since by particle accelerators where unstable particles moving near light speed survive dozens of times longer than they do at rest. Moving objects contract along the direction of motion. Energy and mass are the same quantity in different units. The satellite navigation system in your phone depends on relativistic corrections. Without them, position errors would accumulate at roughly 10 kilometers per day. Einstein extended the framework in 1915 with general relativity, folding gravity into the same picture by describing it not as a force, but as curvature in the geometry of spacetime itself. Clocks deeper in a gravitational field run slower, the effect measured in Boulder with those aluminium ion clocks separated by 33 centimeters, and measured to far greater extremes near neutron stars and black holes. Light bends around massive objects, confirmed during the solar eclipse of 1919, and now used routinely as a tool for mapping dark matter. Gravitational waves ripple through the fabric itself, detected directly in 2015 when the LIGO instruments registered distortion smaller than a fraction of a proton's width, produced by two black holes merging over 1 billion light-years away. This is not a theory on probation. It is among the most thoroughly tested descriptions of nature ever constructed, and it has never failed a test, which is why what Einstein wrote in March of 1955 deserves attention. His lifelong friend Michel Besso had died. The two had met as students, argued physics for half a century, and Besso was the only person Einstein thanked by name in the paper that introduced special relativity. Writing to Besso's family, Einstein offered them what consolation he could, and it was not conventional consolation. He told them that for those who believe in physics, the distinction between past, present, and future is only an illusion, however stubborn. He wrote it as comfort. Read it as a claim about the world, and it says something remarkable. Einstein was not proposing that time is unimportant, or that memory is unreliable, or that we should take a philosophical attitude towards mortality. He was saying that the division of events into the finished, the occurring, and the not yet is a feature of how we experience the universe rather than a feature of the universe. Besso had not stopped existing. He had stopped existing in this region of time, in the same way a city you have left does not stop existing when you leave it. Einstein died a month later. The letter was among the last things he wrote. The question is whether relativity actually forces that conclusion, or whether Einstein was reaching past what his own equations permitted, and answering that requires looking at the geometry his former teacher built out of them, a structure in which space and time are not two things at all. That teacher was Hermann Minkowski, and his relationship with Einstein had not begun well. Minkowski had taught mathematics at the Zurich Polytechnic, while Einstein was a student there, and Einstein had skipped a great many of his lectures, preferring to read physics on his own and borrow notes when examinations approached. Minkowski later described his former student, with some astonishment, as a lazy dog who had never bothered about mathematics at all. Then, in 1908, 3 years after the relativity paper appeared, Minkowski gave a lecture in Cologne that reframed his student's work so thoroughly that Einstein himself needed several years to accept the reframing. Minkowski's opening claim was that from that hour onward, space by itself and time by itself would fade into shadows, and only a union of the two would retain independent reality. It sounded like rhetoric. It was a mathematical result. Here is what he had noticed. Special relativity says that different observers disagree about distances and disagree about durations. Lengths contract, intervals dilate, and the disagreement depends on relative motion. This looks like chaos, as though nothing objective survives. But Minkowski found that a particular combination of the disagreeing quantities does not disagree. If you take the spatial separation between two events and the temporal separation between them, and combine them in a specific way, subtracting one from the other rather than adding, the resulting quantity comes out identical for every observer, regardless of how fast they are moving or in which direction. He called it the interval, and it is the invariant that relativity is built around. Every observer measures a different distance. Every observer measures a different time. Every observer measures the same interval. That is the signature of a geometry. To see why, consider an ordinary map. Suppose two towns sit some distance apart, and you describe their separation using north-south and east-west components. Rotate your coordinate grid. Align it with a road rather than with true north, and both components change. The north-south figure shifts, the east-west figure shifts, and someone using a different grid will write down entirely different numbers. But the actual distance between the towns does not change. Combine the components in the right way, and the rotation cancels out, leaving a quantity everyone agrees on. The relationship between observers and relativity has exactly this structure. Moving at a different velocity is mathematically equivalent to rotating your coordinate grid, not in space, but in a four-dimensional arrangement where time is one of the axes. The disagreements about length and duration are not signs that measurement has broken down. They are the same phenomenon as two surveyors using differently oriented grids and writing down different components for the same fixed separation. What changes is how you slice a single unchanging structure into a spatial part and a temporal part. What does not change is the structure. Minkowski's point, and it is a hard one to absorb, is that if the only frame-independent quantity mixes space and time together, then space and time separately are not fundamental. They are projections. They are what you get when a particular observer, moving in a particular way, carves up a four-dimensional geometry into the parts they call here and the parts they call now. Change the observer's motion and the carving changes. The geometry does not. This structure is called Minkowski spacetime, and it is worth being careful about what it is not. It is not a metaphor. It is not a bookkeeping convenience that helps physicists organize calculations they could have done another way. It is the arena in which special relativity is formulated, and general relativity extends it by allowing the geometry to curve in response to matter and energy. When LIGO detected gravitational waves in 2015, it detected a ripple in this geometry, a passing distortion that stretched one arm of the detector and squeezed the other by a fraction of the width of a proton, exactly as the equations of curved spacetime predict. You do not detect ripples in a bookkeeping convenience. Now, hold the geometry in mind and ask what a moment is. In this picture, an event is a point, a specific place at a specific time, like the flash of a camera or the emission of a photon. Your entire life is not a point, but a line through the structure, a continuous path connecting every event that constitutes you, from the event of your birth to the event of your death. Physicists call it a world line. It does not move. It is a shape extended in four dimensions, in the same way a road is a shape extended across a landscape. The road does not travel. You travel along it, or so it seems, and your present moment, the set of all events you would call now, is a slice through the four-dimensional structure. Take everything happening at this instant, everywhere in the universe, and you have a three-dimensional surface cutting across the geometry. Newton's picture assumed there was one correct way to make this slice, a stack of universal moments piled up like the pages of a book, identical for everyone. Relativity says the slicing depends on your motion. Change velocity and your slice tilts. That word deserves precision because the tilting is not free form and it is not large in everyday circumstances. Walk at a normal pace and your present moment slice rotates by an angle so small that within a room it shifts events by less than the time it takes light to cross an atom. The effect is utterly undetectable at human scales and human distances, which is why nobody noticed it for the entire history of the species. But the tilt is a rotation, and a rotation has a lever arm. Tilt a plane by a fraction of a degree and it barely moves at the pivot. Extend it far enough and the same fraction of a degree lifts one end by a considerable amount. The further from you an event lies, the more your slice sweeps across it as your motion changes. This is where the geometry produces a conclusion that stopped being abstract. The Andromeda galaxy sits roughly 2.5 million light-years from Earth. It is the nearest large spiral galaxy, visible to the naked eye from a dark site as a smudge in the autumn sky. Now, imagine two people on a pavement here on Earth. One stands still, the other walks past at a normal pace, a few kilometers per hour, nothing exceptional. Their relative velocity is trivial. Run the geometry. The walker's slice of the present is tilted relative to the stationary observers by a minuscule angle. Across a room, the difference is nothing. Across 2.5 million light-years, that same angle sweeps the slice through days of Andromeda's history. The two people, side by side on the same pavement, breathing the same air, have present moments that include different events in that galaxy. For one of them, some event in Andromeda has not yet occurred. For the other, walking past at 4 kilometers per hour, it has already happened. This argument was developed independently by C.W. Rayet-Dyck in 1966 and Hilary Putnam in 1967, and it is known as the Andromeda Paradox, or the Rayet-Dyck-Putnam argument. Roger Penrose later gave it a memorable framing by imagining that the event in question is the departure of an invasion fleet. For one pedestrian, the decision has not been made. For the other, the ships are already underway. The point is not the fleet. The point is the logical structure that follows. Suppose you insist that only the present moment is real, that the past has gone and the future does not yet exist. Then reality itself is one of these slices. But which slice? The walkers or the standers? Neither has any claim to priority. Relativity does not merely say we cannot tell which one is correct. It says the question has no answer, because there is no frame of reference with special standing from which to adjudicate. So you face a choice, and both branches are uncomfortable. You can accept that reality is relative, that what exists depends on how you happen to be moving. But existence is not usually the kind of thing that admits of perspective. A galaxy does not partially exist because you took a step. If the walker's present is real and the stander's present is real, and they contain different sets of events, then both sets are real, and reality includes events that one of them calls future. Or you can accept the second branch. All the slices are real. The standers now exists. The walkers now exists. So does the now of someone in a spacecraft moving at a considerable fraction of light speed, whose slice tilts far more dramatically and sweeps through millennia of Andromeda's history. Since there is no privileged slicing, and since every slice is as valid as every other, the union of all possible slices is the whole four-dimensional structure. Everything exists, the block. Rayet-Dyck and Putnam both took the second branch, and Putnam went further, arguing that the philosophical problem of the reality of the future had been settled by relativity, and that no room remained for a genuine ontological distinction between past, present, and future. That was a strong claim, and it did not go unchallenged. But the challenge has to engage with the geometry, and the geometry is not in dispute. There is a subtlety here that critics have pressed, and it deserves to be stated plainly rather than buried. The Andromeda argument relies on chaining relations together. The walker's present includes an Andromeda event. The stander's present includes an Earth event, therefore all of it is real. But the relation is being applied across frames, and one can argue that coexistence, properly defined, should not be transitive in that way. Some philosophers, notably Howard Stein, developed careful responses showing that a coherent notion of a relativized present can be maintained without collapsing into the block. The argument is not a proof, it is a pressure. But notice what that pressure costs to resist. You have to accept that whether something exists depends on your velocity and defend that as a coherent position rather than a contradiction dressed in technical language. There is one more feature of Minkowski's geometry that has to be faced before any of this can be assessed, because it is what stops the whole picture from collapsing into paradox. If your slice of the present can be tilted to include events in Andromeda's future, why can it not be tilted to include events in your own past? Why can you not walk fast enough to bring yesterday back into your now? The answer is a structure built into the geometry itself, and it is called the light cone. Draw a space-time diagram, space running horizontally, time running vertically, and place an event at the center. Now, emit a flash of light from that event. In 1 second, the light has reached every point 1 light second away. In 2 seconds, 2 light seconds. On the diagram, the expanding sphere of light traces out a cone opening upwards into the future. Run the same construction backwards, and a second cone opens downwards, containing every event from which a light signal could have reached the center. 2 cones, meeting at a point. That figure is called the light cone, and it is the skeleton of Minkowski's geometry. Everything inside the upper cone is your future, the set of events you could conceivably influence, reach, or send a signal to, since getting there requires traveling at less than the speed of light. Everything inside the lower cone is your past, the set of events that could have influenced you. And everything outside both cones occupies a region physicists call the elsewhere. Those events are too far away in space and too close in time for any signal to bridge the gap. Light itself cannot cover the distance. Nothing can reach you from there, and nothing you do can reach them. Now, here is the property that holds the entire structure together. The interval, that invariant combination of spatial and temporal separation, comes in three varieties depending on its sign. If the time part dominates, the separation is called timelike, and the two events lie inside one another's cones. If the space part dominates, the separation is spacelike, and each event lies in the others elsewhere. If they exactly balance, the separation is light-like, and only a light signal can connect them. Because the interval is the same for every observer, so is its sign. Every observer, moving at any velocity in any direction, agrees on which events are time-like separated, which are space-like separated, and which lie on the cone. The causal architecture of spacetime is not relative. It is absolute. This is what prevents the whole picture from disintegrating into contradiction. Tilting your slice of the present does not let you sweep your own past into your now, because your past is inside your light cone, and no amount of rotation moves an event across the cone boundary. The tilting only ever sweeps through the elsewhere, through events that are causally disconnected from you in every direction. When the walker on the pavement disagrees with the stander about what is happening in Andromeda, they are disagreeing about a region neither of them can affect and from which neither of them can receive anything. The disagreement is real, and it is quarantined. Causality survives intact. Some philosophers have used exactly this to argue that the Andromeda case is less forceful than it appears. If the events you have supposedly pulled into your present are events you can never observe, never influence, and never learn about until the light has crawled across 2.5 million years, in what sense have you established anything about them at all? The block universe conclusion on this reading is a claim about a region of the diagram that is by construction unreachable. That objection has weight. It also has a limit, and the limit is that the region does not stay unreachable. Wait long enough and the light arrives. Those Andromeda events will eventually enter your past light cone. They will become part of your absolute, undisputed history. So the question is not whether they are real to you now, in some contested sense. It is whether they were real all along, sitting in the geometry, waiting for the light to deliver them. And the geometry offers no mechanism by which they were manufactured somewhere along the way. So we have three coherent positions on the table, and it is worth setting them out precisely, because they are often blurred together and they make very different demands. The first is presentism. Only the present moment exists. The past is gone. Not distant, not elsewhere, but non-existent. The future has not been made. Reality is a single three-dimensional slice, and it is continuously replaced. This is what nearly every human being believes, and it has a long intellectual pedigree. Augustine wrestled with it in the 4th century, observing that the past no longer is and the future is not yet, which seemed to leave existence balanced on a knife edge of vanishing thinness. Presentism has a problem that predates relativity entirely, and it is worth naming because it is not usually the one people expect. If the past does not exist, what makes statements about it true? The claim that a particular battle happened or that you ate breakfast appears to be true or false as a matter of fact. But truth normally depends on something in the world. If the battle has been annihilated, if there is no fact out there for the statement to correspond to, the presentist has to explain what the truth of the claim consists in. Various answers exist, traces in the present, primitive, tensed facts, and none is comfortable. Then, relativity arrives, and the problem becomes acute. Presentism requires a single, universal, correct slice. Relativity says no slice is privileged. This is not a matter of ignorance. The theory does not say we lack the instruments to identify the true present. It says the structure contains nothing to identify. The second position tries to keep what matters most. It is called the growing block, and the philosopher C.D. Broad set it out in 1923. On this view, the past and present are both fully real, but the future is not. Reality is a four-dimensional structure that is genuinely accumulating. New slices of existence are continuously added at the leading edge, and the edge is the present. The past is real, which handles the truth-maker problem cleanly. Your breakfast still exists back there, and that is what makes the statement true. The future is open, which preserves the intuition that tomorrow is not yet settled. It is an elegant compromise, and it fails on the same point. A growing block needs a leading edge, and an edge is a slice, and relativity has no preferred slice. Worse, the edge would have to be a single global surface for the whole universe, which is precisely the object the theory says does not exist. The growing block also carries an objection so peculiar that it took decades to articulate. If past events are fully real, not shadows, but real events with real people in them, then the people in them are as real as you are. And they all believe they are in the present. Every one of them, at every past moment, is thinking exactly what you are thinking now. Which raises an uncomfortable question. What evidence do you have that you are at the leading edge rather than somewhere back in the interior? The philosophers David Braddon Mitchell and Craig Bourne pressed this argument in the early 2000s, and the honest answer is that you have none. Your sense of being present would feel identical either way. On the growing block, you are almost certainly not now. The third position is eternalism, the block universe. All events are equally real. The past has not gone. The future is not waiting to be made. The structure is complete, four-dimensional, and unchanging, and what we call the passage of time is a feature of our position within it rather than a process the universe undergoes. Eternalism fits relativity effortlessly because it makes no demands the theory cannot meet. It needs no privileged slice. Every observer's present is simply their own particular way of carving the structure, and no carving is wrong. The disagreements dissolve because nothing was ever at stake. The events are all there regardless of how you slice them. The price is enormous, and it should not be hidden. On eternalism, nothing ever happens in the sense we mean. There is no becoming. No event is ever brought into existence. The universe does not do anything. It merely is in four dimensions, containing all of it. Now, before this settles into a verdict, there's a move available to the presentist that has to be taken seriously, because it is not obviously wrong. Recall that Lorentz had produced mathematics equivalent to Einstein's while retaining a real ether, a genuine rest frame, a true present, and arguing that motion through it physically distorts rulers and clocks in exactly the way that hides it from us. Lorentz's theory makes identical predictions to special relativity. Every experiment that confirms one confirms the other. They are empirically indistinguishable, and they always will be. So a presentist can say, there is a preferred frame. There is a true universal now. Relativity is correct about every measurement, and the true frame is undetectable in principle, because the very distortions it causes are what conceal it. This is not a cheat exactly. It is a coherent position, and some serious philosophers hold it. But look at what it requires. You must posit a structure that does real work, determines what exists, and is by construction invisible to every possible experiment. Physicists tend to regard invisible structure with suspicion, not because it is forbidden, but because it has a poor historical record. There is one more wrinkle, and it cuts the other way. Our universe does, as it happens, contain a natural slicing. The cosmic microwave background, the radiation left over from roughly 380,000 years after the beginning, fills all of space, and it has a rest frame. You can measure your motion relative to it. Our galaxy is moving through it at something over 600 kilometers per second, which shows up as a slight temperature asymmetry across the sky. On large scales, matter is distributed uniformly enough that a cosmic time coordinate can be defined, and cosmologists use it routinely when they speak of the universe being roughly 14 billion years old. The presentist might seize on this. Here is your preferred slicing. Here is the cosmic now. But it is not privileged by the laws. It is privileged by the contingent arrangement of matter, an accident of how the material happens to be spread out. The equations of relativity treat it no differently from any other slicing, and in a universe with a different distribution of matter, it would not exist at all. Cosmic time is a convenience, not a discovery of the true present. It tells you about the furniture, not the architecture, which leaves the block standing, awkward and unrefuted, and one enormous question unanswered. If the structure is fixed and complete, and if the laws have no preference for one direction over the other, then why does the world so relentlessly point one way? Why does the past feel finished and the future feel open when the geometry says neither is? The answer is not in the equations. It is in a chimney at Manchester and a 19th century argument about heat. The chimney belongs to a brewery, and the man measuring it was not a professional scientist. James Joule was the son of a Manchester brewing family, and in the 1840s, he was conducting experiments of extraordinary delicacy in a place saturated with the noise and heat of industry. His most famous apparatus was almost comically simple: a falling weight, a string, a pulley, and a paddle wheel churning water inside an insulated barrel. As the weight descended, the paddles turned, the water was stirred, and Joule measured its temperature with a thermometer he had built himself, capable of detecting changes of a small fraction of a degree. What he found was that the work done by the falling weight always produced the same quantity of heat. Motion could be converted into warmth at a fixed exchange rate. Energy was not created or destroyed in the process, only transformed. This became the first law of thermodynamics, and it is a conservation law of the kind physics had already grown comfortable with. But Joule's paddle wheel demonstrates something else, and it is the more interesting fact. The weight falls, the water warms. Wait as long as you like, and the water will never spontaneously cool while the weight rises back to the ceiling. Energy would be conserved perfectly if it did. The first law permits it. It simply never happens. This is the second law of thermodynamics, and Rudolf Clausius gave it its central quantity in 1865, naming it entropy after the Greek word for transformation. His formulation was blunt: the entropy of an isolated system never decreases. Heat flows from hot to cold and not the reverse. Concentrated energy disperses, engines lose. Every process in the universe has a cost, and the cost is paid in a currency that only accumulates. Now note what makes the second law unique in all of physics. It is the only fundamental law that distinguishes the future from the past. Every other law is indifferent to direction. This one is not. It is, so far as anyone has been able to determine, the entire physical basis for the arrow of time, for why cups break rather than assemble, why smoke disperses, why you remember your childhood and not your old age, which raises an obvious question. If every underlying law is time-symmetric and matter is made of particles obeying those laws, how does an asymmetric law emerge from symmetric ingredients? Ludwig Boltzmann spent much of his career on this, and the answer he constructed in the 1870s remains standing, though it does not do quite what he initially hoped. Boltzmann's insight begins with a distinction. There's the precise arrangement of every particle in a system, the exact position and momentum of each one, which physicists call the microstate. And there is the coarse description we actually perceive: temperature, pressure, volume, whether the gas fills the room or sits in one corner. That is the macrostate. Enormous numbers of different microstates correspond to the same macrostate, because shuffling individual molecules around usually does not change anything you could measure. But not equally. Consider a room containing air. There are unimaginably many ways for the molecules to be arranged such that the air is spread evenly throughout. Essentially, every random arrangement produces that result. There are vastly fewer arrangements in which every molecule happens to be sitting in the left half, not zero. Just fewer by a ratio so extreme that writing it down requires an exponent with more digits than there are atoms in your body. Entropy, Boltzmann realized, is simply a measure of how many microstates correspond to a given macrostate. High entropy means the macrostate is common. An overwhelming majority of possible arrangements produce it. Low entropy means the macrostate is rare. And now the second law stops being a law at all and becomes a statement of probability. A system in a low entropy state evolves towards higher entropy, not because a law forbids the alternative, but because there are so many more ways to be disordered than ordered that any random wandering through the space of possibilities will find the disordered regions essentially immediately. Gas spreads through a room because almost every arrangement is a spread out one. It is not a force, it is counting. This is a beautiful argument, and its beauty concealed a flaw that Boltzmann's colleague Joseph Loschmidt identified in 1876 in an objection that has never been answered on its own terms. Loschmidt pointed out that the underlying dynamics are time reversible. Take any microstate that evolves towards higher entropy and reverse every particle's velocity. The reversed microstate is a perfectly legitimate configuration, and it will evolve towards lower entropy. The gas will gather itself into a corner, the water will cool while the weight rises. If entropy increases towards the future, because most microstates lead that way, then by the identical argument, entropy should increase towards the past. The counting is symmetric, it does not know which way you are looking. Apply Boltzmann's reasoning to a half-melted ice cube in a glass, using only the laws and the statistics, and it tells you the cube will be more melted in 1 minute. It also tells you the cube was more melted 1 minute ago, that the most probable history is one in which the ice spontaneously assembled from slightly warmer water. This is not a marginal error. It is the argument working exactly as designed and producing an absurd result about the past. So statistics alone cannot deliver the arrow. Something else is needed, and the something else is not a law. It is a fact about how things started. The resolution is to add an assumption that the universe began in a state of extraordinarily low entropy. Given that, and given the statistics, entropy increases in one direction, away from the beginning, and the counting argument is prevented from running backwards because the past is pinned. The philosopher David Albert named this assumption the past hypothesis, and Richard Feynman had made the same point in his lectures, remarking that the only way to understand the asymmetry is to accept that the universe was more ordered in what we call the past, and that this is an additional statement, not a deduction. Sit with what has just happened. The arrow of time, the most pervasive feature of experience, the thing that separates memory from anticipation and death from birth, is not a consequence of the laws of physics. It is a consequence of an initial condition. The rules are symmetric. The setup was not. And the setup was remarkably particular. The early universe was hot, dense, and nearly uniform. And by the ordinary standards of gas in a box, uniformity looks like high entropy, not low. The subtlety is gravity. Gravity is attractive and unscreened, so for a system where gravity dominates, the low entropy configuration is the smooth one, and the high entropy configuration is the clumped one. Matter spread evenly across the early universe was in an exquisitely improbable state with respect to gravity, and the entire subsequent history of structure formation, gas collapsing into stars, stars into galaxies, galaxies into clusters, some material into black holes, is the process of that improbability being spent. Roger Penrose attempted to quantify how special the initial state was, and his estimate is a number so extreme it resists description. The exponent itself requires an exponent. Whatever the precise figure, the qualitative conclusion is robust. The universe began in a condition of staggering statistical rarity, and everything we call the passage of time is the slow relaxation of that condition. Every clock in existence is a device that exploits this gradient. Every memory is a low-entropy record written at the cost of dispersing heat somewhere else. Your brain forming a recollection is thermodynamically identical to a printing press, converting available energy into a stable pattern and waste warmth. Every process that distinguishes before from after runs on the same slope. The reason you cannot remember tomorrow is that the entropy gradient runs the other way, and record-making requires it. Now, bring this back to the geometry, because the two pictures fit together in a way that is easy to miss. If the block universe is correct, the entropy gradient is not something the universe is doing. It is a property the structure has. Slice the four-dimensional block anywhere, and each slice has an entropy value. Those values are low at one end and high at the other. The gradient is a feature of the shape, like the slope of a hillside, present in the landscape whether or not anything is rolling down it. This is why the block does not contradict our experience of direction. The block is not a place where everything is uniform and nothing is distinguished. It is a structure with a pronounced grain. Ask why you remember the past and not the future, and the answer is that memories are records. Records require an entropy gradient, and the gradient in your region points that way. Ask why you were born before you died, and the answer is that your world line is oriented along the same grain. The asymmetry is completely real. It is simply spatial in the four-dimensional sense, a difference between one end of a structure and the other, not a process unfolding. There is a disquieting corollary that Boltzmann himself stumbled into, and it has never quite been disposed of. He speculated, late in his career, that the low entropy region we inhabit might be a random fluctuation, that in an eternal universe sitting mostly at equilibrium, rare downward dips in entropy would occasionally occur, and observers could only exist inside such dips. It is an ingenious idea, and it fails catastrophically. Fluctuations are exponentially penalized by size. If a fluctuation produced us, the overwhelmingly most likely fluctuation is the smallest one consistent with the observation. A single brain, assembled momentarily from chaos, complete with false memories and the impression of a surrounding universe, dissolving immediately. That such an entity would be vastly more probable than an entire orderly cosmos is not a joke. It is a live problem in cosmology, and it functions as a diagnostic. Any theory predicting that most observers are fluctuations of this kind is regarded as thereby refuted, because it undermines the evidence for itself. So we are left with a past hypothesis that works, that explains everything the arrow requires, and that no one can explain in turn. Why the universe began in that state is unknown. It may be a brute fact about the initial conditions. It may follow from something in the physics of the beginning that we have not yet found. What the past hypothesis emphatically does not supply is a flow. It gives a gradient, it gives a direction, it gives an asymmetry. It does not give any moving present, any advancing edge, anything that comes into being. The slope of the hillside is not the rolling of the ball. So where does the rolling come from? If physics offers a static structure with a grain, and experience offers a vivid, continuous, unrelenting sensation of passage, the feeling of moments arriving and departing, then the passage must be manufactured somewhere. And the only remaining candidate is the apparatus doing the experiencing. That apparatus weighs roughly 1.5 kilograms, consumes about 20 watts, and has no organ dedicated to time. This is the first surprising fact about how the brain handles temporal experience. There is a retina for light, a cochlea for sound, receptors in the skin for pressure and temperature. Every sensation you have corresponds to a transducer somewhere, a piece of tissue converting a physical quantity into a neural signal. For time, there is nothing. No structure receives the passage of time and reports it. The sensation of duration, of sequence, of the present arriving and departing is assembled from other things, and neuroscience has spent several decades working out what those things are and how easily they come apart. Start with the delay, because the delay is where the construction becomes visible. Light strikes your retina and the photoreceptors respond, but not instantly. The chemical cascade that converts a photon into an electrical signal takes time. The signal then travels to the thalamus and onto the visual cortex, and processing continues from there. By the time visual information becomes available for anything resembling awareness, something in the region of 80 to 100 milliseconds have elapsed. Sound is faster. The cochlea transduces mechanically, and auditory signals reach cortex in perhaps 10 to 20 milliseconds. Touch on your face arrives quickly. Touch on your toe has to travel the length of your body, adding tens of milliseconds of conduction delay. So the raw sensory data about any single event arrives in your brain smeared across a window of roughly a tenth of a second in an order determined by the physics of your nervous system rather than by the event. Yet you do not experience a stuttering cascade. When someone claps their hands in front of you, the sight and the sound and, if they are close enough, the puff of air all seem to happen together at one instant. The brain achieves this by waiting. It buffers, it collects signals across a window, and then constructs a unified account of what happened, assigning everything a timestamp that reflects its best inference about the external event rather than the arrival time of the data. David Eagleman has described this as living slightly in the past. Awareness runs on a delay, and the delay exists so that the slower channels can be caught up with and integrated. The evidence that this is genuinely happening comes from the places where the machinery makes mistakes. Consider what happens when you look at a clock with a second hand and the hand appears to freeze, that first tick seeming to last noticeably longer than the ones that follow. This is not imagination. It is called chronostasis, and it happens because of how your eyes move. When you shift your gaze, the eye executes a saccade, a ballistic jump lasting a few tens of milliseconds, during which the image on your retina is a useless blur. You never see that blur. The brain suppresses it, and to cover the gap, it takes the image acquired after the saccade lands and retroactively backdates it, extending it to fill the missing interval. The first thing you see after moving your eyes is stamped with a time from before you finished moving them. Land on a clock at the wrong point in its cycle, and the fabrication becomes measurable as a stretched second. The same backdating shows up when the stimulus is not a clock. Present a flash of light alongside a moving object, and observers consistently report the flash as lagging behind, placing the moving object further along its path than it was when the flash occurred. This is the flash lag effect, and the leading explanation is that the brain, having to work with delayed information, extrapolates the position of moving objects to compensate. It predicts. The flash, being unpredictable, gets no such treatment, and the mismatch is what you see. Then there's a demonstration that makes the post-diction undeniable, because in this case, the brain assigns an experience to a moment before the information that produced it existed. Tap a person's wrist several times in quick succession, then their elbow, then their upper arm. What they report is not 3 taps at 3 locations. It is a series of taps marching steadily up the arm at positions where nothing touched them. The phenomenon is called the cutaneous rabbit, and the crucial feature is that the illusory taps between wrist and elbow are placed there only because the elbow tap happened. The brain could not have known where to interpolate until the later stimulus arrived, yet the experience of the intermediate taps is reported as occurring before it. The account was assembled after the fact and presented as if it had unfolded live. None of this is exotic malfunction. It is the normal operation of a system that has to reconstruct events from delayed, staggered, incomplete data and produce a coherent narrative. The narrative is a product. It is not a recording. Now, push further and ask about the present itself, the felt now, the moment you are supposedly inhabiting. William James addressed this in 1890, borrowing a term from an earlier writer and calling it the specious present. His observation was that the present of experience is not a point, it has thickness. When you hear a spoken phrase, you do not experience a knife-edge instant containing one phoneme, with everything before it in memory. You experience the phrase as present, as ongoing, as something you are inside of. James estimated the width of this window at up to several seconds. Modern work has refined that considerably and found structure inside it. There appear to be at least 2 nested scales. At the finer level, sensory events falling within roughly 30 milliseconds of each other tend to be fused into a single perceived moment. Below that threshold, you cannot report which came first, even though you can tell that 2 things happened. Above it, order becomes available. At the coarser level, the brain appears to group events into integrated units lasting something in the range of 2 to 3 seconds. Ernst Poppel argued, this window is a general organizing principle, and the evidence for it is oddly wide. The natural line length in poetry across unrelated languages, the typical duration of a spoken utterance before a pause, the interval at which an ambiguous figure like the Necker cube spontaneously flips, the phrase length in music. The present in this account is not an instant, but a package roughly 3 seconds wide, continuously replaced, which means the moving now you feel is not thin. It is a chunk. And chunks are something a brain constructs, not something it finds. Duration itself is equally constructed and equally unreliable. The brain has no clock in the sense that a laboratory has one. The best current models locate interval timing in the basal ganglia and the striatum and propose that duration is read out of the coincidence patterns of oscillating neurons rather than counted off by a metronome. Whatever the mechanism, its calibration drifts with the chemistry. Dopamine is the clearest lever. Raised dopamine transmission and intervals are judged as longer than they are. The internal accumulation runs fast. Lower it, and intervals contract. This is not a laboratory curiosity. People with Parkinson's disease, whose dopamine-producing neurons are degenerating, show characteristic distortions in time estimation, and the distortions shift when they take their medication. Body temperature affects it too, which was noticed long ago. A person running a fever will overestimate how long a minute lasts, and attention rewrites it wholesale. Present a series of identical images and then an unexpected one, and the unexpected image is reported as lasting longer, though every image was displayed for an identical interval. This is the oddball effect, and it suggests that perceived duration tracks how much processing an event demands rather than how much time it occupied. That finding leads to one of the more instructive experiments in this field, and its value lies in what it failed to find. People who survive car crashes and falls very frequently report that time slowed down, that they perceived the event in detail, unfolding at reduced speed. The report is consistent enough that it invites a physiological explanation. Perhaps under threat, the brain accelerates its sampling rate, taking in more frames per second. Eagleman tested it directly. He dropped volunteers backwards from a tower into a net, a fall of roughly 50 meters lasting about 3 seconds, terrifying enough that participants reliably reported the slow motion effect afterwards. Strapped to each person's wrist was a device displaying digits alternating faster than the eye can normally resolve. If perception genuinely accelerated during the fall, the digits should have become readable. They did not. Nobody could read them. Yet the same people, asked afterwards to estimate the duration of their own fall and of someone else's, consistently judged their own as longer by around a third. The conclusion is precise and it matters. Perception did not slow down. Memory got denser. Under threat, the amygdala engages and lays down a far richer record than usual. And when you subsequently reconstruct the episode, you are reading a thicker file. Duration, in retrospect, is inferred from how much is stored. The slow motion experience is not a recording of the event. It is a judgment made about a recording after the fact, and it is a judgment the brain makes so seamlessly that it feels like a memory of how the moment actually was. Assemble all of it, and a picture emerges that fits the physics with uncomfortable neatness. The brain does not perceive time passing. It holds a state that includes traces of what came before, a model of what is likely to come next, and a running comparison between them. The traces are memories, which exist as physical structures in the present. The predictions are also physical structures in the present. The felt difference between the settled and the anticipated, the sense that one is fixed and the other is arriving, is the difference between a stored record and a forecast, both of which are here, now, in the tissue. Nothing in that requires anything to flow. It requires only that the machinery is sitting at one point along a world line, in a region with an entropy gradient that permits records of one direction and not the other, running a model that treats the record-rich side as done and the record-poor side as open, which appears to close the case, and would, except for one thing. Everything examined so far, the geometry, the entropy, the neuroscience, describes a world of definite events. Quantum mechanics does not. It describes a world in which measurement outcomes are irreducibly probabilistic, in which the result of an experiment appears to be settled at the instant it is performed and not before. If the future already exists, written into the structure, what exactly is being decided when a detector clicks? The detector in question was in Paris, and the year was 1982. Alain Aspect and his colleagues at the Institut d'Optique had built an apparatus to answer a question that had been considered philosophical for half a century. It produced pairs of photons from a cascade in excited calcium atoms, sent them in opposite directions down separate paths, and measured the polarization of each. The critical feature, the one that had taken years of engineering, was that the choice of what to measure on each side was switched while the photons were in flight, fast enough that no signal traveling at light speed could carry information from one detector to the other before both measurements were complete. The results violated Bell's inequality by a margin of many standard deviations, and they did so in the way quantum mechanics predicted. To see why that matters here, the argument has to be reconstructed from its origin, because it began as an attempt to prove precisely the opposite. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics must be incomplete. Their reasoning was careful. Quantum theory permits two particles to be prepared in a joint state, such that measuring one immediately tells you something about the other, no matter how far apart they are. Measure the first, and you know the second. The formalism says the second particle had no definite value until the first was measured. Einstein found this intolerable, and his objection was not aesthetic. If the particles are far enough apart that no light signal could pass between them, then measuring one cannot physically affect the other without something traveling faster than light, which relativity forbids. Therefore, they argued, the second particle must have had a definite value all along, and quantum mechanics simply fails to record it. There must be additional information, hidden variables, that the theory omits. Reality is definite. The description is incomplete. It is a strong argument. Its premises are reasonable. And for nearly 30 years, it looked like a matter of taste, since both pictures made the same predictions. Then, in 1964, John Bell, an Irish physicist working at CERN who thought about foundations in his spare time, found a way to make it an experimental question. Bell's move was to consider measurements along different axes rather than the same one. Suppose each particle carries hidden instructions specifying what result it will give for any possible measurement setting. Bell showed that if such instructions exist, if the values are definite in advance, and if what you choose to measure on one side does not influence the other side, then the correlations between the two sets of results must satisfy a certain arithmetic constraint. The constraint is not a feature of any particular theory. It follows from the assumptions themselves. Quantum mechanics predicts correlations that exceed the constraint. This converted a philosophical dispute into a laboratory measurement, and the laboratories answered. Aspect's experiments in the early 80s were the first convincing demonstrations. Every subsequent refinement has confirmed them, and the refinements have been thorough because each early experiment left a gap an ingenious skeptic could exploit. Perhaps the detectors were only sampling a biased subset of pairs. Perhaps the settings were not chosen independently enough. In 2015, 3 separate groups closed the remaining major gaps simultaneously in a single experiment, one of them using electron spins in diamond, separated by more than a kilometer across the campus at Delft. The violation held. Aspect, John Clauser and Anton Zeilinger received the Nobel Prize for this work in 2022. So one of Bell's assumptions is false. The question is which? The usual reading is that the definite values were never there, that the particles genuinely had no polarization until measured, and quantum indeterminacy is a feature of the world rather than of our knowledge. This is the standard position, and it appears to threaten the block universe directly. If the outcome of a measurement is genuinely undetermined until it occurs, then the future is not written. There is nothing in the structure to write. But notice the assumption sitting quietly inside Bell's derivation, the one that is almost never questioned, because it seems too obvious to state. Bell assumed that the experimenter's choice of measurement setting is independent of the properties of the particles being measured. He assumed the two are uncorrelated, that the decision to turn the dial one way rather than another has nothing to do with what the photons were carrying. In a universe that flows where the future is generated moment by moment, this is nearly unarguable. The experimenter decides the particles were emitted earlier, A later free choice cannot be correlated with an earlier state without something very strange going on. In a block universe, it is not obviously true at all. The block contains the emission event and the setting choice and the detection, all as part of one four-dimensional structure. The structure must be consistent throughout. There is no rule requiring that the parts of a fixed geometry be statistically independent of one another. Indeed, the entire structure is threaded with correlations imposed by the requirement that everything fit together. This possibility has a name. Physicists call it superdeterminism, and it is treated with more hostility than perhaps any other position in foundations. Bell himself considered it and set it aside, remarking that it would make the notion of free experimentation meaningless. The standard objection is that it appears to undermine science. If your measurement settings can be correlated with what you are measuring, no experiment establishes anything. That objection is powerful, but it is not a refutation, and Sabine Hossenfelder has argued at length that the hostility outruns the reasoning, that superdeterminism only looks absurd if you have already assumed the very thing at issue, namely that the future is open and choices are uncaused. The debate has not been settled, it has mostly been avoided. There is a related and more disciplined version of the idea, and it deserves to be distinguished carefully. Retrocausal interpretations propose that the measurement setting influences the particle's earlier state, that causal influence runs backwards as well as forwards along the world line. This sounds outrageous until you recall that the fundamental laws are time-symmetric, at which point the outrage becomes harder to justify. If the equations do not distinguish direction, why should influence? John Cramer developed one such account in 1986, the transactional interpretation in which a measurement is completed by waves traveling forwards and backwards, in time meeting in a handshake. Hugh Price has argued for decades that retrocausality is the natural reading of a time-symmetric physics, and that resisting it requires importing an asymmetry the equations do not contain. And a result, by Matthew Leifer and Matthew Pusey in 2017, sharpened the picture considerably. They proved that under reasonable assumptions, you cannot have a time-symmetric account of quantum theory without retrocausality. One or the other must go. These are minority positions, but they exist because the block universe and quantum indeterminacy do not fit together comfortably, and something has to give. There is a third route, and it is the one that has gained the most ground among physicists who think seriously about this. It does not modify relativity or invoke backwards causation. It denies that anything indeterminate ever happens. Hugh Everett proposed it in 1957 as a doctoral student at Princeton. His observation was that the mathematics of quantum theory contains an equation describing how a quantum state evolves, and that equation is smooth, deterministic, and time-symmetric. It contains nothing about measurement. The apparent randomness enters only through an additional rule, the collapse postulate, asserting that upon measurement, the state jumps discontinuously to one outcome. Everett asked what happens if you simply delete that rule and let the equation run. The answer is that nothing collapses. The measuring device becomes entangled with the system, and the observer becomes entangled with the device, and the result is a state containing every outcome, each correlated with a version of the apparatus that registered it and a version of the observer who saw it. The outcomes do not compete, they coexist in branches that no longer interact. Everett's thesis was received badly, and he left academic physics. It is now taken seriously by a substantial number of working physicists, in part because decoherence, a well-understood and experimentally confirmed process by which quantum systems lose their capacity to interfere once they interact with a complex environment, explains why the branches stop influencing one another. Decoherence is not a hypothesis. It is measured routinely, and it is the central practical obstacle in quantum computing. If Everett is right, then the block universe survives intact and simply becomes larger than anyone imagined. There is no randomness to be squeezed into a written structure. Because there is no randomness, every outcome occurs. The four-dimensional block contains all branches, complete, and the sense that one particular result happened to you is a fact about which branch that version of you occupies. Randomness is what determinism feels like from the inside, when the inside is one branch among many. The cost is a universe of staggering multiplicity and a well-known difficulty about probability. If every outcome happens, it is not obvious what it means to say one was more likely than another. Serious work has gone into answering this, and the answers are contested. So the confrontation between quantum mechanics and the block does not produce a verdict. It produces a menu. Accept genuine collapse and the future is open, but you must explain how a collapse, an instantaneous global change in the state, is supposed to work in a relativistic universe with no privileged slicing, a problem that has never been solved cleanly. Accept superdeterminism or retrocausality, and the block survives, at the cost of assumptions most physicists find unpalatable. Accept Everett, and the block survives entirely, enlarged beyond recognition. What no one has produced is a way to have collapse, relativity, and an open future all at once, coherently, which leaves the question of what a written universe would actually contain. Not whether it can be reconciled with quantum theory, but what it means for tomorrow to already be there, in full, in detail, down to the words you have not yet chosen. Consider a sentence that Aristotle worried about in the 4th century before the Common Era, in a short passage in his treatise on interpretation. The sentence is, "Tomorrow there will be a sea battle." Aristotle's question was not about naval tactics, it was about truth. Every statement, according to the logic he had built, is either true or false. So take that sentence today before any battle. If it is true, then the battle will happen, and nothing anyone does can prevent it, because if it could be prevented, the statement would be false. If it is false, the battle will not happen, and no admiral's decision can bring it about. Either way, the outcome appears to be settled before anyone has done anything, and human deliberation looks like theater performed over a script. This is logical fatalism, and it is worth separating carefully from everything else in this discussion, because the two get confused constantly and they are not the same problem. Fatalism says the outcome is fixed regardless of what happens in between, that you will die on a particular day whether or not you take the medicine, that the battle occurs whether or not the fleets sail. Determinism says nothing of the kind. Determinism says the outcome follows from the prior state through the operation of the laws, which means the medicine and the sailing are part of what produces it. Under determinism, your actions are not bypassed. They are the mechanism. Remove them and the outcome changes. The block universe is often heard as fatalism, and that hearing is wrong. The block contains your deliberation. It contains the weighing of options, the hesitation, the decision. If those were different, the structure would be different. Nothing in a fixed geometry implies that the parts do not depend on one another. Quite the reverse, since the dependencies are what make the geometry consistent. So the sea battle problem is not a physics problem. It is a problem about what makes statements about the future true. And Aristotle's own answer was to suggest that statements about contingent future events may not yet have a truth value at all. A move that has troubled logicians ever since, because it requires abandoning the principle that every statement is either true or false. Now leave logic and return to physics, because there is a second confusion that needs clearing, and it concerns what determinism does and does not give you. In 1890, Henri Poincaré was working on a problem that had been posed as a prize competition by the King of Sweden. Is the solar system stable? Will the planets continue in their orbits indefinitely, or will the accumulated tugs between them eventually throw one out? Poincaré attacked the simplest hard version, the motion of three bodies under mutual gravity, and what he found changed the character of the question. There is no general closed solution. The trajectories can be so intricately tangled that arbitrarily small differences in starting conditions lead to entirely different outcomes. He noted that this was not a limitation of his technique. It was a property of the system. The result sat largely unabsorbed for 70 years until a meteorologist at the Massachusetts Institute of Technology encountered it by accident. In 1961, Edward Lorenz was running a simplified computer model of atmospheric convection. Wanting to examine a portion of a run more closely, he restarted the calculation partway through, typing in the values from a printout rather than beginning again from the start. The new run tracked the old one for a while, then diverged, and within what corresponded to a couple of simulated months, the two weather patterns had nothing to do with one another. The cause was mundane. The computer held 6 decimal places internally. The printout showed 3. Lorenz had entered a number differing from the original by less than 1 part in 1,000, a discrepancy far smaller than any real measurement of the atmosphere could resolve. He published the analysis in 1963, and in 1972 gave a talk with a title that supplied the field its permanent image, asking whether the flap of a butterfly's wings in Brazil could set off a tornado in Texas. The crucial feature of Lorenz's system is that it is completely deterministic. There is no randomness in it anywhere. Every future state follows rigidly from the present one through fixed equations, and it is unpredictable in practice permanently because the precision required to forecast it grows exponentially with the interval you want to forecast. To extend a weather prediction from 1 week to 2, you do not need slightly better data. You need data better by orders of magnitude, and the requirement compounds without limit. So determinism and predictability come apart entirely. A universe can be rigidly fixed and completely opaque to any calculation performed inside it. That last clause matters more than it first appears. Any predicting device is made of matter, occupies space, and processes information at a finite rate. Seth Lloyd worked out the physical limits in 1999 and again in 2002, calculating the maximum computation the observable universe could have performed since the beginning, given its energy content and its age. The figure is enormous but bounded, and it is smaller than what would be required to simulate the universe in detail, which is exactly what you would expect, since a complete simulation of a system needs to encode the system, and no subsystem can encode the whole. Stephen Wolfram named the general principle computational irreducibility. For many systems, there is no shortcut. You cannot leap ahead to the answer. The only way to find out what a system does is to let it do it, step by step, and the doing is not faster than the thing itself. Put these together, and something interesting emerges about what a written future would be like from inside. It would be indistinguishable from an open one. There is no experiment that reveals the writing, no calculation that outruns events, no vantage from which the structure is visible as a structure. Even a fully determined universe presents itself to its inhabitants as a sequence of surprises. Now to the point that most often goes unnoticed, and it is the one that clarifies what the block is actually claiming. The block universe does not require determinism. This sounds wrong, and it is worth going slowly. Determinism is a thesis about laws, that the state at one time, together with the laws, fixes the state at all other times. Eternalism is a thesis about existence, that events at all times are equally real. These are different claims, and neither entails the other. You can have determinism without eternalism, a presentist world where only the present exists, but each present is rigidly produced by the last. And you can have eternalism without determinism, a four-dimensional structure containing genuinely chancy events where the outcome at a given point is not fixed by anything earlier, but is nonetheless there, in the structure, as a matter of fact about what the structure contains. That second combination is the one people find hardest to hold in mind, and it is entirely coherent. Imagine the block includes a radioactive atom that decays at a particular moment. Suppose nothing whatsoever determined that moment. No hidden variable, no prior cause, genuine, irreducible chance. The decay still occurred at that moment. The event is still located in the geometry. The structure still contains it. What the structure does not contain is a reason. So a block universe with real quantum randomness is possible. The events are all there. Some of them simply have no explanation in terms of what came before. This is why the confrontation in the previous section did not produce a knockout in either direction. Indeterminism threatens determinism. It does not obviously threaten eternalism, because eternalism was never a claim about causes. Which brings us to the word that has been doing quiet damage this entire time. Already. The future already exists. Tomorrow is already written. These phrases have been used throughout, and they are, strictly speaking, malformed. Already is a tensed word. It means, as of now, before the expected time. It presupposes a moving present against which things can be early or late, Apply it to a four-dimensional structure, and you have imported the very thing the structure denies. Saying the future already exists is like asking what is north of the North Pole. The words are grammatical, and the question is empty. The block universe's actual claim is subtler and less lurid. It is that existence is not a tensed notion at all. When a mathematician says that prime numbers greater than 1 trillion exist, they do not mean the primes exist right now, at this instant, as opposed to some other time. The claim has no temporal index. Eternalists say the same about events. Your death exists in the way that a mountain on the far side of a continent exists. Not now, not yet, but simply, without a time attached. This deflates a great deal of the picture's drama, and it also makes it harder to attack. The eternalist is not claiming that tomorrow is happening somewhere, waiting to arrive. They are claiming that the question of what is happening depends on a slicing, that no slicing is privileged, and that the structure containing all slicings is the thing that is real. Ted Sider put the position carefully in his work on four-dimensionalism, and the careful version is the one worth engaging with. Objects on this account are extended in time in the same way they are extended in space. You have temporal parts just as you have spatial parts. The version of you reading this is a part of you, in the same sense that your hand is a part of you. You are not wholly present at any moment. You are a four-dimensional shape, most of which is not here. That formulation has a strange consequence, and it is the one that everything has been building towards. If you are a shape rather than a process, if the whole of you is laid out and every decision you will make is a feature of your geometry, then what happens to the thing you experience most directly, several times an hour, which is the feeling of choosing? In 1983, Benjamin Libet published a result from his laboratory at the University of California, San Francisco, that has been argued about ever since. And the arguing has been productive because most people have the result backwards. The experiment was simple in design. Volunteers sat with electrodes on their scalps, watching a spot of light travel around a circular face like a fast clock hand. They were asked to flex their wrist whenever they felt like it. No cue, no schedule, spontaneous. And to note the position of the spot at the moment they first became aware of the urge to move. Meanwhile, the electrodes recorded electrical activity from the motor areas of the cortex, and a sensor on the wrist recorded when the muscle actually fired. Neuroscientists already knew about a signal called the readiness potential, a slow buildup of activity in the supplementary motor area that precedes voluntary movement. What Libet measured was its timing relative to the reported moment of conscious intention. The readiness potential began, on average, about 550 milliseconds before the muscle moved. The conscious urge was reported about 200 milliseconds before the muscle moved. The brain had started organizing the action roughly a third of a second before the person was aware of deciding to perform it. The result was taken immediately and widely as evidence that free will is an illusion, that the decision is made unconsciously, and awareness arrives afterwards, like a press office issuing a statement about a policy it did not set. That reading has not survived scrutiny well, and the reasons are worth stating, because they illustrate how difficult this territory is. Aaron Scherger and colleagues proposed in 2012 that the readiness potential may not be a decision signal at all. In their model, cortical activity fluctuates continuously, and when a person is waiting to move at an arbitrary moment, the movement is triggered when this ongoing noise happens to cross a threshold. Average the recordings backwards from the movement, and you will always see an apparent ramp. But the ramp is an artifact of averaging, assembled from fluctuations that were going to happen anyway. On this account, the readiness potential does not cause the action. It is the shape of accumulated randomness, viewed in retrospect. Libet himself never claimed to have refuted free will, and he pointed to a residual window. The urge was reported 200 milliseconds before the movement, which leaves time to cancel it. He called this the veto, but set the interpretive disputes aside because they are not the point here. The point is what Libet's experiment does to the question, regardless of which reading wins. Notice that both the deflationary reading and the defensive reading share an assumption. Both take for granted that the interesting question is about timing, whether the conscious intention arrives before or after the neural preparation, whether awareness is in front of the process or trailing it. That framing only makes sense if there is a fact about what is happening at each successive instant, with one thing genuinely causing the next as time advances. In a block universe, the timing question does not go away, but it stops being the question. The readiness potential and the conscious intention and the wrist flexion are all events in the structure, arranged in a particular order, and the order is a feature of the geometry. Asking whether the neural activity got there first is asking about the shape. It is not asking whether anything was free, because in the block, nothing is arriving anywhere at all, which forces the real issue into the open. The threat to free will was never neuroscience. It was never even determinism, exactly. It is something more basic, and it has a name that has been in circulation since the 17th century. The traditional framing runs like this. If every event follows necessarily from prior events plus the laws, then your decision to raise your hand follows from your brain state a second earlier, which follows from your brain state a minute earlier, and so on back through your childhood, your birth, and the arrangement of matter before you existed. At no point in that chain is there a place for you to intervene. The chain passes through you, but you did not author any link of it. This is the standard incompatibilist argument, and Peter van Inwagen gave it its sharpest modern form in 1983, calling it the consequence argument. Its structure is austere. If determinism is true, our actions are consequences of the laws of nature and events in the remote past. But it is not up to us what went on before we were born, and it is not up to us what the laws of nature are. Therefore, the consequences of these things, including our present acts, are not up to us. Every step looks unobjectionable. The conclusion is that free will and determinism cannot both be true. The compatibilist response, which is the majority position among philosophers who work on this, attacks the phrase "up to us." It argues that the incompatibilist is using a notion of freedom that nothing could possibly satisfy, not determinism and not indeterminism either. To see the force of this, run the argument the other way. Suppose determinism is false. Suppose your decisions are not fixed by prior states, that genuine quantum randomness enters somewhere in your neural processing and the outcome is undetermined until it occurs. Has anything been gained? Your hand rises because a probabilistic event resolved one way rather than another. That is not authorship. It is a dice roll wearing your name. Nobody has ever explained how randomness could deliver control, because randomness is precisely the absence of control. So the dilemma closes from both sides. If your actions are determined, they were fixed before you existed. If they are undetermined, they are arbitrary. Neither one delivers the kind of freedom the incompatibilist wants, which suggests that the kind of freedom being wanted may be incoherent, a demand for actions that are neither caused nor uncaused. The compatibilist proposal, developed carefully by Daniel Dennett across several decades, is that this demand was always confused, and that what people actually care about when they care about freedom is something else entirely. They care about whether their actions flow from their own deliberation rather than from coercion, whether they could have done otherwise had they wanted to, whether they are responsive to reasons, whether presenting an argument or a threat or new information changes what they do, whether they are the author of their actions in the sense that the actions express their values and their evaluation of the situation. All of that is perfectly compatible with a determined universe, because all of it is about the character of the process rather than its ultimate origin. A person who deliberates, weighs, considers consequences, and acts accordingly is doing something categorically different from a person who is drugged or coerced or seizing. The difference is real, and it is measurable, and it is exactly what our practices of responsibility track. Now, bring this into the block, because the block changes the emphasis in a way worth noticing. In a flowing universe, the anxiety about determinism has a temporal shape. Something in the past reached forward and made you do it. The past is doing the compelling. That image is what gives the consequence argument its emotional weight, the sense of being pushed from behind by events you had no part in. Remove the flow, and the pushing disappears. There is no forward reach because nothing reaches. There is a four-dimensional structure in which your deliberation occupies a region, and the events after that region depend on the deliberation in the sense that a different deliberation would mean a different structure. The relationship between your thinking and your acting is not weakened by the block. It is exactly as strong as it ever was, because it was always a relationship between parts of a pattern rather than a transfer of force through time. Put it this way. When you say you could have done otherwise, you are saying that if the deliberation had gone differently, the action would have been different. That conditional is true in the block. It is true in a determined universe. It is what could have done otherwise has always meant in ordinary use, because nobody, asked whether they could have taken a different route home, is asking whether the initial conditions of the universe were adjustable. But the block does take something, and it should not be papered over. It removes the openness. It says, the future is not a space of possibilities waiting to be narrowed by your choice, but a region of the structure that is what it is. Your deliberation is real, it matters, it is doing genuine work, and its outcome is a fact about the geometry, and the geometry is not being written as you go. There is a version of this that people find easier to accept, and it comes from looking backwards. Consider a decision you made 10 years ago. It is settled now. Nothing you do can change it. Does that settledness make your deliberation at the time a sham? Almost everyone says no. You thought about it, you waited, you decided, and the fact that the outcome is now fixed does nothing to reach back and hollow out the process. The block universe asks you to extend that judgment in the other direction. If fixedness does not undermine the reality of a past deliberation, it is not clear why it should undermine a future one. The asymmetry in your reaction is an asymmetry in your knowledge, not in the events. Whether that argument succeeds is a matter of ongoing debate, and it should be. But it clarifies what is actually at stake, and the stake is not agency. It is a particular picture of agency, one in which the future is a fog that our choices condense into fact. There is one more thing the block does, and it is the one that people encounter first, usually without any of the preceding machinery. Because if the structure contains all of it, then it contains the people who are gone. The people who are gone are, on this picture, still there. Not in memory, not in influence, not in any metaphorical sense. They occupy a region of the structure, doing what they were doing, and the structure is complete. This is the part of the block universe that arrives without warning. Someone reads about relativity and simultaneity and light cones, and somewhere in the middle of the geometry, a personal implication surfaces that the geometry did not announce. Einstein's letter to the Besso family was exactly this collision, a technical claim about the equations pressed into service as consolation by a man writing to people who had just lost someone he had argued with for 50 years. It is worth asking whether the consolation is honest, because it is easy to overclaim here, and overclaiming would be a failure of the same rigor that got us this far. Consider what the block actually says. A person is a world line, a four-dimensional shape extended along the time axis, beginning at one end and terminating at the other. Death, in this description, is not an annihilation. It is a boundary. The world line has an end in the way a road has an end, and the road does not cease to exist at the point where it stops. Every event along it remains an event. Every moment of a life remains located in the structure, unaltered, permanent in the only sense the block permits, which is not that it lasts forever, but that it is. Now notice what that does not include. It does not include continued experience. The person is not somewhere, having thoughts, waiting. Experience is a process that occurs along a world line, and where the world line ends, the process ends. There is no vantage point from which the deceased observes their own permanence, because observing is something that happens at particular locations in the structure, and their locations are all in the past. It does not include reunion or access or any change in your situation. You cannot reach them. Their region and your present are separated by the same geometry that separates you from every other event outside your light cone, with the additional constraint that they lie in your past, causally settled, receding. and it does not include comfort of the kind people usually want. What it offers instead is a claim about ontology, that the past is not nothing. That when we say someone is gone, we may be making a mistake about the meaning of the word, treating the present slice as the whole of reality when the physics gives no warrant for privileging it. That is a real claim, and it is not empty. But it is thinner than it first appears, and honesty requires marking the difference. The philosopher Derek Parfit approached this from an entirely different direction and arrived somewhere adjacent, which is interesting because his route had nothing to do with physics. Parfit argued that personal identity is not what matters, that the thing we care about when we care about our own survival is psychological continuity and connectedness, and that these come in degrees rather than in a binary. There is no deep further fact about whether a future person is you. There are only the relations. Parfit reported that this conclusion changed his attitude to his own death. He described the walls of a glass tunnel dissolving, the tunnel through which he had been moving faster each year, with blackness at the end. When he stopped believing in a separate self, persisting through time, the prospect of ceasing seemed to matter less. Others would have experiences after his death, and it was no longer clear to him why the absence of a particular relation between those experiences and his present ones was worth the dread. Set Parfit's argument beside the block and they are describing the same terrain from opposite sides. Parfit dissolves the self that time was supposedly carrying. The block dissolves the carrying. Both leave the events, the experiences, the moments, the deliberations, exactly where they were. Now examine the emotional structure, because there is something worth understanding here that is not about physics at all. Why does death feel like loss in a way that non-existence before birth does not? You did not exist for something on the order of 14 billion years. That absence produces no distress in anyone. Lucretius made this observation in the 1st century before the Common Era and used it as an argument. The time after your death is a mirror of the time before your birth, and since the second causes no suffering, the first should not either. The asymmetry in our reaction, he argued, is a failure of consistency rather than a response to a real difference. The argument has been debated for 2,000 years and has not been settled. Parfit pushed on it with a thought experiment. Imagine learning that a painful operation you underwent is behind you, versus learning that an equally painful one lies ahead. Almost everyone prefers the first, which shows that we are not neutral about temporal direction even when the quantity of suffering is identical. We care about the future more than the past, and it is not obvious that this preference is rational rather than merely deep. The block universe makes that asymmetry look even stranger. If past and future are equally real, and the difference between them is a matter of which way the entropy gradient runs and where your records are, then the enormous asymmetry in how we regard them is a psychological fact rather than a metaphysical one. We are built to care about the direction our records do not cover. That is a feature of organisms that need to survive, not a discovery about the structure of time. None of this is an argument that anyone should feel differently about death. Reasoning of this kind does not reliably reach the parts of a person that grieve, and it would be dishonest to suggest that a correct view of spacetime geometry is a treatment for loss. Einstein's letter was written by a man who was himself dying, offering what he had, which happened to be physics. What the block does offer is a change in the description. It says that the phrase "no longer exists" contains a tense, and the tense presupposes a structure the physics does not support. It says that a life is not a thing that happened and then stopped happening, because happening was never the right verb. It says that if you ask where someone is, the answer is not nowhere. The answer is there, at those coordinates, as much a part of the structure as this sentence. Whether that is consolation or merely accuracy is a judgment each person makes for themselves. Physics does not adjudicate it. There is one more consequence that follows from the same reasoning and cuts the other way, and it should be stated because omitting it would be selective. If the block is real, then everything that has ever gone wrong is also permanent. Every atrocity is a fixed feature of the structure. Every suffering that has occurred is not erased by having passed. It is there, at its coordinates. part of the geometry, exactly as real as the moment you are in. The consolation about the dead and the horror about the suffering are the same claim viewed from two angles. You cannot accept one and decline the other. This is not a reason to reject the block. The universe is not obliged to be comfortable, and choosing a physical model by its emotional consequences is precisely the error that scientific method exists to prevent. But it is a reason to be suspicious of anyone who presents eternalism as a warm idea. It is not warm. It is symmetric. And symmetry is exactly what makes the picture so difficult to abandon, because every attempt to install a preferred moment, a real present, a genuine becoming, has failed on the same rock. Relativity does not contain the resources to specify which moment, unless, of course, the geometry has places where it stops behaving, places where the smooth structure that carries all of this reasoning breaks down entirely, and the equations that describe spacetime return answers that are not numbers. Those places exist, and the first one was found in a trench. Karl Schwarzschild was a 41-year-old astronomer serving in the German army on the Russian front in 1915, calculating artillery trajectories when Einstein's field equations were published. Within weeks, he had produced the first exact solution, a description of the geometry of spacetime around a spherical mass. He sent it to Einstein, who was startled that anyone had found a closed solution so quickly, and presented it to the Prussian Academy on Schwarzschild's behalf. Schwarzschild died of an autoimmune disease contracted at the front a few months later. His solution contained something nobody wanted. At a particular radius, determined entirely by the mass, terms in the equations went to infinity. At the center, they did it again, and worse. The outer one turned out to be a false alarm. It took decades of work to establish, but the surface at that radius, the event horizon, is not a place where physics fails. It is a place where a particular coordinate system fails, in the way that longitude becomes meaningless at the North Pole without anything unusual happening to the ice. An astronaut crossing an event horizon feels nothing. There is no wall, no membrane, no local signal. For a sufficiently large black hole, the tidal forces at the horizon are gentler than standing on Earth. What the horizon marks is not a physical structure, but a fact about the causal geometry. From inside, every future-directed path leads inwards. The singularity is not a location you could steer away from. It is a moment in your future, as unavoidable as next Tuesday. That reframing is worth pausing on, because it is a direct statement about the block. Inside a black hole, the roles of space and time in the Schwarzschild solution effectively exchange. The radial direction becomes timelike. Falling towards the center is not traveling somewhere, it is aging. The singularity is not down, it is later, which means the geometry can bend so severely that the distinction between a direction in space and the direction of time depends on where you are standing. And if the difference between those two is a local feature rather than a global fact, the claim that time is a dimension rather than a process becomes harder to dismiss as a mathematical convenience. The inner infinity is a different matter. At the center of the Schwarzschild solution, curvature grows without bound, and this is not a coordinate artifact. No change of variables removes it. Roger Penrose proved in 1965 that this was not a peculiarity of the idealized spherical case, that under very general conditions, once a region has collapsed past a certain point, singularities are unavoidable. Stephen Hawking extended the theorems to cosmology, and together they demonstrated that general relativity, taken at face value, predicts places where it stops being able to say anything. A theory that predicts its own breakdown is telling you something. Usually, it is telling you that a deeper theory is required and that the breakdown marks the boundary of the current description rather than a feature of the world. The singularity is almost certainly not real. It is a signal that at sufficiently extreme curvature, general relativity must give way to something that incorporates quantum mechanics, and no such theory has been completed, which is the crux of the difficulty, and it is not a technical detail. It is a conflict about what time is. General relativity treats time as a dimension of a dynamic geometry, curved by matter, with no preferred slicing and no universal parameter. Quantum mechanics, in its standard formulation, treats time completely differently, as a fixed external background parameter, universal, marching along in the equation that describes how states evolve. Position in quantum mechanics is an observable, something you measure, with an operator attached. Time is not. Time is the thing the evolution is written against. These are not two descriptions that need reconciling at the edges. They are incompatible at the root. The most direct attempt to combine them produced a result so strange that physicists have been arguing about it for over half a century. In 1967, Bryce DeWitt and John Wheeler wrote down an equation intended to describe the quantum state of the entire universe, applying the standard quantum procedure to general relativity. The equation has no time in it. The time variable does not appear. What emerges is a constraint on the state of the universe, a condition it must satisfy, with nothing describing evolution, because in a theory where the geometry itself is the thing being quantized, there is no external clock left to evolve against. This is called the problem of time, and it is not a minor irritant. It is a structural feature of the most straightforward route to quantum gravity. Physicists have responded in several directions. Some argue the equation is telling the truth, and time is genuinely absent at the fundamental level, emerging only as an approximation for subsystems large enough to serve as clocks. Don Page and William Wooters proposed a mechanism in 1983 in which the universe as a whole is static, but is internally correlated in such a way that one part of it, functioning as a clock, is entangled with the rest, and conditional on the clock reading a value, the rest appears to be in a corresponding state. Time, on this account, is not a background. It is a correlation. The universe does not evolve. It contains internal relationships that look like evolution when examined from inside. This was tested in a limited way. In 2013, a group in Italy built a small experimental analog using entangled photons, with one photon serving as the clock and the other as the evolving system. An observer using the clock photon saw evolution. An external observer, looking at the joint state, saw nothing changing at all. The experiment does not prove the Page-Wooters mechanism describes the universe. It demonstrates that the mechanism is not incoherent, that a static whole containing an apparently dynamic part is a thing that can actually be constructed. If that is what is going on, the block universe is not merely compatible with quantum gravity. It is what quantum gravity is describing. Other approaches disagree sharply. Loop quantum gravity, developed by Carlo Rovelli, Lee Smolin, Abhay Ashtekar, and others since the 1980s, quantizes geometry directly and finds that space is granular, that area and volume come in discrete units with the smallest possible size around the Planck scale. Rovelli's reading is that time is not fundamental but relational, and he has argued this at length. Smolin, who helped build the theory, has moved in the opposite direction and now argues that time is the only thing that is fundamental and that the laws themselves may evolve. Two of the field's founders, working on the same theory, drawing opposite conclusions about the nature of time. That is a reasonable indicator of how settled this is. Now to the extreme case, where the disagreement becomes concrete. If the singularity at the center of a black hole is not real, something replaces it. Some approaches suggest the collapse halts and reverses, that a bounce occurs at the smallest scales and the interior connects to an expanding region. Applied to cosmology, the same reasoning suggests the beginning of our universe might not have been a beginning at all, but a bounce from a prior contracting phase. That possibility bears directly on the past hypothesis. If the low entropy initial condition that gives us the arrow of time is not an initial condition but a transitional one, then the question of why entropy was low becomes a question about what came before, and the arrow may point in different directions on either side of the bounce. Some models propose exactly this: two universes emerging from a single low entropy point, arrows pointing away from each other, each set of inhabitants regarding the other as its past. And there is one further piece of geometry that has to be confronted, because it was found by someone who understood these equations better than almost anyone. In 1949, Kurt Gödel, the logician who had demonstrated the incompleteness of formal arithmetic, turned his attention to general relativity. in part because he and Einstein were walking home together from the Institute for Advanced Study most days and had been discussing it. Gödel constructed an exact solution to the field equations describing a rotating universe. In that solution, the rotation drags the light cones around so severely that paths exist which are timelike throughout, always moving into the local future and yet return to their starting event. A closed timelike curve, a world line that loops. Gödel's universe is not ours. It rotates, and observation indicates ours does not. It has no expansion, and ours expands. But that was never his point. His point was that the field equations permit such a solution, which means that the impossibility of returning to your own past is not a consequence of relativity. It is a contingent fact about the particular geometry we happen to inhabit. And Gödel drew a conclusion from this that he presented to Einstein directly. If the equations permit a universe in which the past is a place you can return to, then in such a universe, the past clearly must exist. You cannot travel to nothing. But the existence of the past cannot be a contingent matter, dependent on the rotation rate of your particular cosmos. Therefore, Gödel argued, time does not flow in any universe, including this one. The lapse of time is an illusion everywhere, and his rotating solution was the proof. Einstein's response was cautious. He acknowledged the solution was troubling and suggested such configurations might be excluded on physical grounds. They have not been. Similar solutions have been found repeatedly since, around infinitely long rotating cylinders, in the geometry of cosmic strings, in traversable wormhole configurations. Every one of them requires conditions we have no evidence exist, but none has been ruled out by a principle. Hawking proposed in 1992 that the laws of physics might conspire to prevent closed time-like curves, a chronology protection conjecture which he suggested would keep the universe safe for historians. He could not prove it. 30 years later, nobody has. So the picture at the extremes is this. The geometry that supports the block universe breaks down in exactly the places where we would most want to test it. The theory that would replace it has, in its most direct formulation, no time at all, and the equations permit, without apology, worlds in which the past is a destination. Which leaves one question, the one that has been implicit since the beginning. If all of this is true, if the structure is fixed, if the flow is manufactured, if the equations describe a shape, then how would we ever know? Begin with what would count as evidence, because the honest answer is that no experiment has ever been performed whose outcome depends on whether the block universe is true, not one. And this is not a temporary state of affairs awaiting better instruments. The eternalist and the presentist agree on every prediction because they are not disagreeing about what will be measured. They are disagreeing about what the measurements describe. That fact has led some physicists to dismiss the whole question as empty, a dispute about words dressed in geometry. The dismissal is too quick, and the reason it is too quick is that the positions do not have equal standing with respect to the theories we already have. Eternalism asks for nothing that relativity does not supply. Presentism requires a preferred slicing, and a preferred slicing is a physical structure. Structures leave traces. They can be hunted. The hunting has been going on for a century, and it has become extraordinarily precise. The direct descendants of the Michelson-Morley apparatus are now optical resonators, crystalline cavities cooled to a few degrees above absolute zero, in which light bounces between mirrors of astonishing perfection. Rotate the cavity, and if the speed of light depends on direction, the resonant frequency shifts. Modern versions have found no shift at a sensitivity of roughly 1 part in a billion billion. If there is a preferred frame, it is hiding at a level far below anything Lorentz imagined he was concealing. Astronomy provides a longer lever. In May of 2009, the Fermi Space Telescope recorded a gamma-ray burst catalogued as the one from the 10th of that month, an explosion in a galaxy roughly 7 billion light-years away. The burst emitted photons across an enormous range of energies. Several proposals for quantum gravity suggest that at fine enough scales, the geometry of spacetime is granular rather than smooth, and that this granularity should make the speed of light depend slightly on energy, high-energy photons dragging fractionally like light through glass. Over 7 billion years, even a minuscule dependence would separate the arrivals by a wide margin. They arrived within a fraction of a second of each other. The constraint that produced is severe enough to rule out the simplest versions of energy-dependent light speed, right up to and past the scale where the granularity was supposed to appear. Spacetime, as far as we can measure it across most of the observable universe, is smooth. None of this proves the block. What it does is close doors on the alternative one by one, and the closing has been relentless. But there is one place where the question becomes genuinely testable, and it is worth being precise about why, because this is where the argument stops being philosophical and acquires a laboratory. Recall the difficulty with quantum collapse. If measurement genuinely produces a definite outcome out of an indefinite state, and if that transition is a real physical event, then it happens across space instantaneously, which requires a slicing to be instantaneous with respect to. That is a preferred frame, smuggled in through the back door of quantum mechanics. Standard quantum theory avoids the problem by declining to say that collapse is physical. Objective collapse models do not decline. They propose that the transition is a real process governed by new physics, occurring spontaneously and more frequently the larger a system becomes. And those models make predictions. If collapse is a physical process, it jostles particles. A jostled charged particle radiates. So an objective collapse theory predicts a faint spontaneous emission of radiation from ordinary matter that is doing nothing at all. Matter sitting in the dark, undisturbed, quietly glowing at a rate no conventional physics permits. That is a measurement you can make, if you can build somewhere quiet enough. The Gran Sasso Laboratory sits beneath more than a kilometer of rock in the Apennine Mountains, shielded from cosmic rays by the mountain itself. In 2020, a collaboration operating a germanium detector there reported the results of a search for exactly this radiation, and the result was negative at a level sufficient to exclude the simplest parameter-free version of the gravity-related collapse model that Lajos Diosi and Roger Penrose had independently proposed. The model was not killed outright. It has adjustable parameters, and the parameters retreated, but the space it can live in shrank considerably. This is the shape of the future here. Not a decisive experiment on the nature of time, but a slow constriction of the alternatives conducted underground, in silence, by people counting individual photons that mostly do not arrive. And notice the logic of it. If objective collapse is ever confirmed, if someone measures that glow, then something in the block universe has to break. There would be a real physical process defining a real global present, and the geometry would have to accommodate it. If collapse continues to fail every test, the alternatives to the block continue to thin. So the question is not unfalsifiable. It is indirect, and it is slow, and it is being answered by proxy. What remains is a set of admissions, and they should be stated plainly rather than dressed up as mystery. We do not know why the universe began in a state of such extraordinarily low entropy, and every explanation of time's direction rests on that unexplained fact. We do not know how to write down a quantum theory of gravity, and the most direct attempt produced an equation with no time in it. We do not know whether the singularities in the equations are real or are signals of our own incompleteness, and we cannot go and look. We do not know whether the geometry permits closed loops in time, and we cannot rule them out. We do not know what happens at the center of a black hole, and the answer is behind a horizon by construction. Two of the founders of the same theory of quantum gravity have concluded, from the same mathematics, that time is not fundamental, and that time is the only thing that is. That is the actual state of the field. Not a consensus that reality is fixed and complete, but a description that keeps working, that has never failed a test, that contains no flow, and that nobody has found a way to improve. What can be said with confidence is narrower than the headlines suggest, and more interesting. There is no universal present, that is measured, not argued. The equations contain no passage, that is arithmetic. The arrow we experience comes from an initial condition, rather than from a law. That is the best explanation anyone has produced in 150 years of trying. And the sensation of a moving now is assembled by a nervous system that demonstrably backdates, interpolates, and reconstructs, and that has no organ for the thing it reports so insistently. Whether the structure containing all of it is complete in 4 dimensions, or whether something is being added at an edge we cannot locate, is not currently answerable. It may become answerable. It may not. What is worth holding on to is the peculiarity of the position we are in. A species assembled from matter, embedded in the structure, seeing it from one location along a single line, using instruments made of the same material, has managed to establish that its most immediate and universal experience does not correspond to anything in the mathematics of the world it inhabits. That is not a failure of physics. It is a measurement of the distance between how the universe works and how it feels to be inside it, taken from the inside, with no way to step out. Wherever your world line runs, this moment is part of the shape. Whether it is passing or simply there is a question that has been open for 100 years, and the answer, if there is one, is somewhere in the structure already.